Black holes have long been described as some of the most terrifying objects in the universe, regions so dense that not even light can escape their gravity. For decades, they were thought to be fundamentally unknowable, with their interiors hidden forever behind a one-way boundary. But recent advances in observational astronomy, particularly through the James Webb Space Telescope, have brought us closer than ever to these cosmic enigmas. This telescope has captured data that may help uncover what lies inside black holes. What it found is challenging the very foundations of what scientists believed, with implications that could reshape the future of physics. When most people hear the term black hole, they tend to imagine a dark, bottomless pit. In reality, a black hole is far more complex, with multiple layers, each more extreme than the last. The outermost layer is the event horizon. This is not a solid surface, but a conceptual boundary marking the point of no return. Once anything, matter, or light crosses this line, it cannot escape. Though you wouldn't feel anything upon crossing it, to an observer watching from a distance, time would appear to slow down and eventually freeze at the horizon, as astrophysicist Kip Thorne once explained. The event horizon is not just a place in space, it is a moment in time. Once inside, nothing can change your fate. Just beyond the event horizon is the accretion disk, a swirling ring of superheated gas and dust spiraling inward. The material here heats to millions of degrees as it's pulled in, emitting intense X-ray radiation. This radiation is one of the few ways we can detect black holes, as the glowing disk lights up before its contents disappear into darkness. It's similar to watching a spotlight beam before the bulb is swallowed by shadow. Farther in lies the photon sphere, a region where gravity is strong enough to trap light in circular orbits. Light here doesn't escape, instead, it endlessly loops around the black hole. If you were somehow suspended in this zone, you would see strange distortions, including a warped image of your own back. Deeper still is the singularity, the core of the black hole, where all known laws of physics collapse. Gravity becomes infinite, and space and time as we know them cease to exist. While classical physics describes this as a point of infinite density, other theories suggest that it may be something else entirely, such as a Planck star, a theoretical object where quantum forces prevent full collapse. But because no information escapes the singularity, we may never know its true nature. As one physicist put it, black holes are where the universe seems to divide by zero. This layered structure transforms black holes from mere mysteries into deeply complex phenomena. To truly grasp them, we have to look at their origins. Black holes are formed through dramatic cosmic events. The most common type, called stellar mass black holes, form when a massive star many times heavier than our sun runs out of fuel. Without the outward pressure from nuclear fusion to counteract gravity, the core collapses within seconds, compressing into an extremely dense point. This implosion often results in a supernova explosion bright enough to outshine an entire galaxy. What's left behind is a black hole. However, not all black holes are born from stars. In the early universe, before stars had time to form and die, enormous clouds of hydrogen gas hundreds of thousands of times the mass of our sun collapsed directly under their own gravity. These created what are known as direct collapse black holes, and they may have become the seeds for the supermassive black holes found at the centers of galaxies today. These early black holes were fed by rivers of gas flowing through the cosmic web, an enormous network of matter that connects galaxies across the universe. In one remarkable observation, astronomers discovered a black hole surrounded by 6 galaxies, all connected by these filaments, suggesting a period of intense growth in the early cosmos. One of the enduring puzzles is how some black holes grew so quickly. Astronomers have found black holes weighing billions of solar masses just 900 million years after the Big Bang. The rapid growth is difficult to explain. One scientist compared it to finding a baby that weighs 200 pounds. The key to their rapid development may lie in the structure of the cosmic web, which funnels matter efficiently into the hearts of growing black holes. Once formed, black holes do not remain passive. They interact with the universe in violent and often destructive ways. particularly when stars or planets come too close. Although black holes do not seek out their prey, anything that drifts too near is at risk. One of the most violent interactions occurs during a tidal disruption event. When a star ventures close to a black hole, the difference in gravitational pull between its near and far sides stretches it into a long strand of hot gas process, known as spaghettification. Part of the star may fall into the black hole, while the rest is ejected outward in a spectacular flare. This phenomenon has been observed from far away as 665 million light-years. As for planets, the chance of Earth being pulled into a black hole is extremely low. Black holes are small compared to the vastness of space, and most are located far from us. Nonetheless, in dense star clusters where stars are packed closely, smaller black holes could potentially capture planets that stray too near. These planets would become trapped in orbits around an invisible object, turning into so-called rogue worlds. Black holes are also found in binary star systems, where one of the two stars has collapsed into a black hole. These systems provide invaluable insight because the black hole's gravity pulls matter from its companion star, heating the material and producing X-rays that can be observed. The first confirmed black hole, Cygnus X1, is part of such a pair. We cannot see the black hole itself, but its presence is inferred from the way it affects its companion. On a larger scale, black holes don't consume entire galaxies. While they are incredibly powerful, even the largest supermassive black holes account for only a tiny fraction of their galaxy's total mass, less than 0.01%. Instead of devouring their host galaxies, they help shape them. As black holes feed on nearby gas, they emit powerful energy in the form of jets and winds, which can prevent surrounding gas from cooling and forming new stars. This process, known as AGN feedback, acts like a thermostat that regulates galactic growth. During galactic mergers, black holes at the centers of colliding galaxies can also merge, producing gravitational waves ripples in spacetime that we've only recently begun to detect with instruments like LIGO. Interestingly, not all the matter that falls toward a black hole is consumed. Some is hurled back into space at near light speeds through high-energy jets. These jets can stretch thousands of light-years and push gas away from the galactic center, showing that black holes can act as engines of cosmic evolution. In truth, galaxies don't fall into black holes. Rather, black holes emerge and grow at their centers, guiding the evolution of their surroundings. For many years, what happened inside a black hole was considered unknowable, a mystery sealed behind an event horizon. That changed in 2010, when the Event Horizon Telescope (EHT) produced the first image of a black hole's shadow, captured from galaxy M87, about 55 million light-years away. This wasn't an image of the black hole itself, but of the dark silhouette it created in glowing light around it. The ring of light came from the accretion disk, and the center was the shadow. More recently, the James Webb Space Telescope has contributed further by studying the behavior of gas and dust as it falls into black holes. While Webb cannot take direct images like EHT, it excels at observing in infrared, allowing it to peer through cosmic dust and capture details never before seen. By studying how matter accelerates and heats up near the event horizon, astronomers can reconstruct the physical structure of this boundary region. Computer simulations also play a major role in black hole research. Using Einstein's equations and supercomputers, scientists can simulate what happens to light and matter as they fall inward, predicting warped visuals, extreme turbulence, and the formation of features like the photon ring, a narrow band of light that orbits just above the event horizon. Future upgrades to EHT may allow us to observe this ring directly. Another tool, called X-ray reverberation mapping, measures how X-rays bounce off the inner regions of the accretion disk. These echoes allow scientists to estimate the disk's structure and infer the black hole's spin. Each echo represents a fleeting glimpse into the chaos near the edge. At the heart of the mystery lies the singularity itself. According to classical physics, this is a point of infinite density where all known laws break down. But infinity in science often signals a problem in our understanding. It suggests that our current theories cannot fully describe what is happening. Some researchers propose that the singularity may not exist at all. In theories such as loop quantum gravity, the collapsing matter might reach a limit where quantum forces prevent further compression, resulting in a Planck star dense, minuscule object rather than an infinitely small point in this view. The black hole might even eventually rebound, reversing the collapse over unimaginable timescales. Another major mystery is the information paradox. According to quantum mechanics, information about particles can never be lost, but general relativity suggests that information falling into a black hole disappears forever. This contradiction has sparked intense debate.